So last time we talked about limits of polynomial functions. Today we're going to discuss rational functions. These are expressions that are ratios of polynomials. And they cause slightly different situations to arise, particularly when the denominator turns out to be 0. There are actually two different situations. One is a case where there's a factor upstairs and downstairs and they cancel to some extent so that it's not in the denominator. And that gives rise to a hole in the graph. And the other situation is referred to as an infinite discontinuity, which graphically are shown as vertical asymptotes. So we'll discuss those separately because they're a little different. Rational functions don't have to have these features at all. They may or may not. It all depends on the actual graph. For example, if you have y equals 1 over x squared plus 1, for example, well, the denominator is never 0, and the actual graph so it looks a little bit like this, symmetric about the y-axis, and it's asymptotic to the x-axis. But there are no holes, there are no vertical asymptotes. It's continuous everywhere. As we proceed, it's going to be important to be working, though, with fractions on occasion. And if we have a situation where we have positive numbers and a is less than b, we want to be able to take reciprocals. And when you take reciprocals, it reverses the direction of the inequality. So 1 over a becomes bigger than 1 over b. And this is not something that you would typically remember. There's not much reason to use it too often before now. But you might want to keep in mind a simple little example that will help you to be able to keep track of this. If 2 is less than 3, when you take reciprocals, a half is going to be bigger than a third. And so as long as you have in mind numbers actually like this, it can be helpful to be able to figure out what's going on. So rational functions are continuous at points that are not zeros in the denominator. So here's the rational function 1 over x, and the graph is as shown. It has a vertical asymptote at the line x equals 0, which is the y-axis. But you notice it is continuous at the point where x is equal to 5. So I'd just like to show you what's involved in a proof of that. It's somewhat similar to what we had before with polynomials. So to prove continuity at that point, we want to show that the limit 1 over x as x approaches 5 is equal to 1/5. So our definition is going to involve, for any epsilon greater than 0, there's a delta greater than 0, and this implication is going to have to be satisfied. And as we did before, in order to write a proof, we have to concentrate on the last part of the definition. So working backwards, we can write that 1 over x minus 1 over 5. If we put this all over a common denominator, we'll have 5x downstairs, and then upstairs is 5 minus x. The absolute value of a quotient is the same as the quotient of the absolute values, so you can split that up that way. And the distance between 5 and x is the same as the distance between x and 5. So the absolute value can always be expressed either way. There's a little result we've had in pre-calculus: absolute a minus b equals absolute b minus a. The way this works, by the way, is that absolute a minus b is the same as 1 minus 1 times absolute b minus a. And so this is the same thing as the absolute value of minus 1 times the absolute value of b minus a. And of course, that's equal to 1, the absolute value of minus 1. So at any rate, we'll be using those things as we go along. And one other thing that we do need to work with is the idea that if we have an interval that's centered at x equals 5, we need to exclude all denominator zeros. Now, the denominator 0 is occurring at x equals 0, so we need to find an interval, I don't care, any interval about centered at 5. So here's x plus delta, and here's x minus delta. And we just have to have the interval such that it excludes x equals 0, which is not difficult to do. So that means that it's 5 units away from 0, and so any number less than 5 is going to do the job. So to be definite, we'll take delta equals 3. So when we have absolute x minus 5 less than delta, less than 3, that's equivalent to saying that the value of x minus 5 is between minus 3 and plus 3. So if you add 5 to all sides, you'll end up with the inequality that x is between 2 and 8. Now, you'll notice that we have x in the denominator, so we need to bound 1 over x. And in order to do that, we want to take reciprocals of 2 less than x, because when we take reciprocals, we'll get a half is bigger than 1 over x. So that gives us the bound on 1 over x. So we can now rewrite the last term over there, x minus 5 over 5x. I can split up the x minus 5 over 5 and leave as a multiplication 1 over absolute x. Well, the x's we're interested in are in the interval, they're all positive, so 1 over x is the same, in absolute value is the same as 1 over x. And so this is going to be less than the 1/2 that I just got, because we took delta equals temporarily the number 3. And so finally we have this inequality. So what does that mean? Well, if we solve this inequality for absolute x minus 5 on the left, it's a matter of multiplying both sides by 10. So we'll get absolute x minus 5 is also has to be less than 10 epsilon. So as before, first we took a temporary value of 3, and then we found a bound on x minus 5 that we additionally needed. Here it's 10 epsilon. So we choose delta equals the minimum of 3 and 10 epsilon. And with that in mind, we can write the proof. The proof is straightforward. Given epsilon greater than 0, choose delta equals the minimum of 3 and 10 epsilon, in which case, if x satisfies this inequality, then delta is less than or equal to 3, which means, as we showed, x minus 5 is between minus 3 and 3, x is between 2 and 8. So we now can write the inequalities as I had before, that absolute 1 over x minus 1 over 5, which was the thing we wanted to show we can make less than epsilon by choosing delta appropriately. So we showed that that's less than this number and this number. And because we additionally have that absolute x minus 5 is less than or equal to 10 epsilon, this last step over here is going to be less or equal to 10 epsilon over 10, which is equal to epsilon. And that completes the proof for showing, in a simple case, continuity for a rational function.